pleasure to introduce our DXCS distinguished speaker, seminar speaker today, Dr. Peter Clark from Oregon State University. I prepared this and he said that I'll keep it short, so who he is and where he's from. So, but I still need to mention, like, he's one of the leading author of the IPCC first report in the sea level change section. And I'll save some time for this wonderful talk, so let's give him a big hand.
Thank you. Thanks, Tony. That's good. So thank you very much, Chuning and Vince, for helping organize my trip out here. It's my first time to Rutgers, but of course I know many people here directly or indirectly, and among other things, the work that I do, there's a lot of overlap with people who are here. And with regard to this topic of sea level rise, you know, Rutgers really is, as many of you know, an epicenter of sea level research in the United States. So it's a really great opportunity to come here and talk about this subject. So the title is Sea Level Rise Over the Next 100 to 10,000 Years in Response to Global Warming, an update to AR5. Those of you not familiar what AR5 is, that stands for the Fifth Assessment Report by the IPCC, or the Intergovernmental Panel on Climate Change. And I was involved in that AR5 with the chapter on sea level change. Bob Kopp will be involved in the next assessment, the Sixth Assessment Report on that, on dealing with sea level change, not a chapter specifically on that, but he'll be working on that subject, representing that field. So I'm going to give a bit of an update to AR5, and this is by far from comprehensive because the chapter on sea level change dealt with many different aspects of sea level, of which almost all of them have seen much progress in the literature and the science since the AR5, which the timeline of release of the AR5 was of our working group 1 was in September of 2013. So we're already approaching 5 years since its release. And so in that time, there's been a lot of progress in a number of different aspects of sea level change. And I'm just going to focus on the projections side. So the, this was working, just a minute. Have to be closer. I swear to God it was working. Well, okay, manually it goes. Okay, so this is an outline of the talk. So we'll first of all talk briefly about what the main contributions are to global mean sea level rise, and I specify global mean sea level rise to distinguish it from regional sea level, which is a whole nother topic in itself that again we addressed in the assessment report. So we're just talking about the global mean sea level rise. And then I'll go into what the AR5 projections were for the 21st century. And then I'll provide updates, some updates on those projections that have been done since publication of the AR5. And then we're going to go into the long-term projections, and this is an area in which there's been also a lot of new work done since the AR5. And we're going to go out to 10,000 years in the future, and I'll show you why, and that's why we're interested in that. And then briefly some of the implications of this, and then some take-home messages at the end. So starting with contributions to global mean sea level rise. So this is a cartoon showing the different components of sea level and the things that cause sea level to change. And the main things that we're interested in here are, first of all, the warming of the ocean itself as heat is uptaken into the ocean, and that causes thermal expansion. And then there is loss of land ice, and this is glaciers and ice sheets, losing mass into the ocean and causing sea level to rise. And then finally, there's reduction of liquid water storage on land. And the emphasis I'm going to place here is mostly on the land ice component of it with respect to changes in our understanding and its contributions. But I'll go through some of the numbers for each of these contributions that we came up with. So I do want to spend a little time, though, on the land ice component. And so when we look at glaciers and ice sheets and how they contribute mass to the ocean and cause sea level to rise, I don't know why this stopped working. It's too bad. Is there another pointer? Yes. Rather than that big stick?
That's the dipstick.
The dipstick, yeah.
That's a distinguished.
Thanks, Yair. So first of all, looking at glaciers and ice sheets, we look at two aspects of glaciers and ice sheets. One is the surface mass balance. And this is simply looking at the amount of mass that accumulates on glaciers and ice sheets, largely as snow. And then the mass that's lost from the surface of glaciers and ice sheets through melting processes. Okay, so that's what we'll be calling surface mass balance. And then the other part of the equation with respect to land ice or glaciers and ice sheets is the loss of mass, in this case, loss of mass through dynamics. And this is basically solid ice discharge that occurs from the ice sheet or glacier directly into the ocean and causing, in this case, sea level to rise. Now, in this particular case, we're looking at the grounded ice sheet that's grounded. The base of the ice sheet is below sea level, and sea level is shown over here, and this is the ocean. And in this case, the ice sheet is coming out of the area where it's grounded, and it goes afloat here into an ice shelf. And that location where it goes afloat is called the grounding line. So it's simply where the ice goes ungrounded out into the ocean or becomes grounded as you go into the ice sheet. And in these particular situations, as shown in this cartoon, it's not uncommon for the ice sheet to be on the bed of the bedrock that is sloping in under the ice sheet away from the ocean. And this particular configuration gives rise to a potential instability of the ice sheets that can be triggered by climate change, but once it is triggered, then it becomes sort of self-sustaining instability that causes discharge of solid ice into the ocean and is a mechanism by which we can lose ice relatively quickly. And so I'm going to go through this mechanism briefly here, and this mechanism is called the marine ice sheet instability, and we're going to just refer to this as MISI, M-I-S-I. And so here is that configuration again of a grounded ice sitting on a reverse sloping bed, reverse sloping back into the ice sheet. There's the grounding line, and there's where it goes afloat into an ice shelf. And what happens is if you were to trigger the grounding line by some mechanism to start moving backwards down this slope, then you will trigger this MISI mechanism. And the way that works is that you can trigger this mechanism by thinning the ice shelf and losing the buttressing that that ice shelf provides to the ice sheet, or simply by eroding the grounding line position as you bring warm water in under the cavity of the ice shelf and causing that grounding line to migrate down the slope in this direction. But once that happens, then what happens is the grounding line now at a new position is coincident with where the ice sheet is now thicker. And the thickness, greater thickness of the ice then increases the flux of the ice, because the flux of the ice is a function of its surface slope and the thickness of the ice. And that increases the flux of the ice through the grounding line and discharging ice into the ocean, which then causes the grounding line to retreat further, because the increase in flux of the ice causes the ice to thin, so then it goes afloat again at the grounding line and retreats back down the slope. And so then finally, it continues in this direction, and now it's self-sustaining as long as it's in this reverse bed slope configuration. So again, you have retreat down the slope, the ice is thicker, you increase the ice flux, the ice thins and retreats backwards. So this is the marine ice sheet instability, and this is, as we'll see, has been the emphasis or focus of a lot of interest in how ice sheets can contribute to sea level rise relatively quickly. Okay, so now we'll get into projections, and most of you are aware of how the projections were made for AR5 was by using these representative concentration pathways, or RCPs, of which there were 4. And they're labeled here RCP 2.6, 4.5, 6.0, 6.0, and 8.5. And on the left is showing for the 21st century, on the horizontal axis, the emissions of carbon associated with these 4 scenarios in colors. And then on the right is the corresponding increase in CO2 in the atmosphere for each of these 4 scenarios. And so the RCP 2.6 involves strong mitigation and lowering and going into negative emissions by the end of the century, whereas RCP 8.5 is the business as usual type of situation or scenario where we continue to emit carbon at a high rate and causing CO2 concentrations to increase through the century and beyond. And so we'll be talking about mostly the RCP 8.5, the higher end scenario, because this is what captures most interest with regard to sea level change, for example. But this gives you the flavor of the 4 different scenarios that were assessed with respect to, in our case, sea level change. So let's get right to the projections for global mean sea level rise that we came up with. Shown on the time series here, graph on, is showing for the 21st century is global mean sea level in meters, so this is 1 meter. And in red with the orange band, uncertainty band around it, is the RCP 8.5 projection through this 21st century for RCP 8.5. And in blue is the sea level rise in the mean of the ensemble and then the uncertainty band for the RCP 2.6, the low end scenario. If we get to the numbers, then for RCP 8.5, this high-end scenario, we come up with a likely range, and I'll talk about what we mean by likely in a minute. But the likely range for global mean sea level rise by 2100 was, we came up with 0.53 to 0.98 meters. So let's just say 1 meter upper end of the likely range for this. And if we looked at the rates of sea level rise by the end of the century, we were looking at, there we go. Rates of sea level rise of 8 to 16 millimeters per year, whereas today we're around 3 millimeters per year. So acceleration of sea level rise through the century giving rise to this amount of sea level rise. Now, what do we mean by the likely range? This is a calibrated language that's used in the IPCC to talk about a probability of the sea level reaching this amount of about 66 to 100% probability. And that's what's called the likely range. What this means is what's often overlooked is that there's about a 1/3 probability that sea level can be higher or lower than this likely range. Okay, so when we give you those numbers of 0.53 to 0.98 meters for RCP 8.5, that 0.98 is not the maximum sea level projection we're giving you. We're giving you the likely range. And we're not saying that sea level couldn't get higher. In fact, we're saying there is a possibility of that being the case. But the reason we did not go to a higher probability at the time was for 2 reasons. One, we could not assess the very likely range, which was a 90 to 100% range, because the surface air temperature projections were also presented in the likely range, and we use those for thermal expansion and surface mass balance. And for looking at ice sheet dynamical contributions, we just didn't have information that we felt confident enough to quantify the probability of a very likely range or a range higher than our likely range from that contribution, okay? But the important point to keep in mind is that we're not excluding the potential for higher sea levels. And that's, of course, what the big question is how much higher it could go. So I'm not gonna spend any time on this slide other than to show that we came up with the likely ranges for all of these different components, thermal expansion, land, water, glaciers, the ice sheet, surface mass balance, and dynamics. And the other main important point of our chapter that we made 5 different places, 5 different places in the chapter though, was that when we looked at current understanding of all the different contributions and the possible amounts that they could contribute, we concluded that only the collapse of the marine-based sectors of the Antarctic ice sheet would cause sea level, global mean sea level, to rise substantially above the likely range. And that's only during the 21st century. So the message here is that when we look back at that previous slide of all the different likely ranges, of all those likely ranges, we felt confident that they represented truly what the sea level contribution was going to be from those components. And that the only way you're going to get above the likely range was if the ice sheet, the Antarctic ice sheet, became unstable through this marine ice sheet instability mechanism, through dynamics, where it's marine-based, and that occurred this century, and thus started to contribute to sea level, and that would give sea level rise higher than our likely range, only from that contribution. And so if we look again at what the contribution we came up with for the likely range from Antarctic ice sheet dynamics, this is the likely range. And we're saying that of the total likely range of sea level rise, this would be the only mechanism by which you would exceed that if we were to start contributing from Antarctica through dynamics, okay? So this is really the main source of uncertainty in the AR5 projections, is what is Antarctica gonna do? in our conclusions. And furthermore, though, we did try to assess what that contribution from Antarctica could be if it started to become unstable in the 21st century. And again, we didn't have enough confidence in the numbers that are out there to give a very likely range for that distribution, but we concluded that with medium confidence, again, this is calibrated language by the IPCC, that it would not exceed several tenths of a meter during the 21st century. Okay, kind of vague, several tenths of a meter, but what it's doing is it's saying not a meter during the 21st century, not 2 meters during the 21st century, somewhere less than a meter during the 21st century. Okay, so very important point, again, something that's often overlooked in interpreting the chapter, even though this point was repeated multiple times throughout the chapter. So those are the projections. That's the likely range for the high-end scenario RCP 8.5, with that caveat that we're only going to exceed that likely range if Antarctica ice sheet becomes unstable this century, in which case it's only can contribute several tenths of a meter of sea level rise. Okay, now let's go to the update. And one thing I forgot to mention is that the projections I showed you were based on process-based models. That is, models that are based on physics of the process, thermal expansion, ice sheets, glaciers, surface mass balance, and so forth. There are other types of models of sea level rise that we assessed, but we made our assessment of what the sea level rise would be based on these process-based models. And that's what I'm going to continue to focus on here, is what has happened to our understanding of sea level rise based on process models since the AR5. So let's look first at the Greenland ice sheet. And I mentioned that we felt that of all the different components to sea level rise, we felt fairly confident that they all remain within their likely range, except for Antarctica and through dynamics. But let's look at Greenland anyway, because it's another big ice sheet. And this is the likely range we came up with, the median value of 0.15 by the end of the century. Median value of 0.15 with a likely range of 0.09 to 0.28 meters. And let's look at studies that have been done since then. And these are just 4 studies that I've found that give the amount of sea level rise from Greenland by the end of the century. And without going into the details, you can see the numbers here all fall pretty well within the likely range, if not actually below it. Okay, so again, this is supporting our inference, if you will, or our conclusion that for Greenland, it's unlikely we're going to exceed the likely range during the 21st century, and process-based models that have been published since then are supporting this conclusion. In fact, they're indicating that our high end of our likely range might be even higher, too high. Okay? So that's the main point there. Now let's go to Antarctica and reiterate our conclusion that only the collapse of marine-based sectors, if initiated this century, could cause global mean sea level rise to rise substantially above the likely range during the century. Okay? And if that was the case, then it would be higher than the numbers we came up with. So the report was released in fall of 2013. In 2014, these 3 papers were published. The main conclusions of these 3 papers were that the marine ice sheet instability mechanism had likely become, or had started from Antarctica. Okay, so our conclusion bit that we would only exceed that if this mechanism initiated during the 21st century. A year after we released the report, 3 papers came out and said, it's begun, okay? So what does that mean? So, again, this is our likely range shown above without the marine ice sheet instability mechanism, the MISI mechanism involved, but with an allowance of several tenths of a meter if MISI was to start this century. And then these are the 3 main papers that have been published since that include MISI, the marine ice sheet instability mechanism, in very sophisticated models of the Antarctic ice sheet, or parts of it. And they are suggesting that the contribution from ice dynamics involving MISI during the century is in this range here. And you can see it's on the order of a few tenths of a meter, okay? So that was consistent with our allowance in terms of understanding from these physical models. And the big quote, though, I want to bring out here is this last paper published by Catherine Ritz in 2015, right at the end of 2015, said this: given current understanding, plausible predictions of Antarctic ice sheet instability leading to greater than 0.5 meters of sea level rise from that instability mechanism of MISI, by 2100 would require new physical mechanisms. In other words, they felt that the understanding of MISI at that point was sufficient to say that it was not going to exceed this amount that is within our allowance, and only if something else new came along would it exceed that. Now, I wonder if they knew something was in the works, because a few months after this paper was published, drum roll, a new physical mechanism was introduced. And this was introduced in this paper by DeCanto and Pollard in Nature that has become very well known, which is titled Contribution of Antarctica to Past and Future Sea Level Rise. So let's look at this paper in some detail. First of all, the mechanism itself that differs from MISI is whereby you have sufficient surface warming on ice shelves fringing the Antarctic ice sheet that in many places are providing key buttressing support to the ice sheet to prevent dynamical ice sheet response and rapid sea level rise. So sufficient surface melting develops during the century that causes the ice shelf to collapse, and this is demonstrated as having happened on the Antarctic Peninsula in 2002 with the collapse of the Larsen C or Larsen B ice shelf here at that time, where basically the surface meltwater on the ice shelf caused the ice shelf to collapse. And that leads then to what they call the marine ice cliff instability. So versus MISI, we now have MICI, okay? So let's look at MICI a little more detail. And so here we go. Here's MICI in the nice cartoons provided by DeCanto and Pollard. So here is, again, our grounded ice sheet below sea level. There's the ice shelf. And now we start to warm up the climate enough to cause surface meltwater on the surface of the ice shelf, which then causes the ice shelf to crevasse, and the water that accumulates in the crevasses hydrofractures through the ice shelf and causes it to collapse rapidly, as we saw happen with the Larsen ice shelf on the Antarctic Peninsula some years ago. Okay, so once that happens, now you have removed the ice shelf and the buttressing support it provides, and that initiates MISI. Okay, so now the ice sheet is no longer buttressed, so it starts to retreat down that reverse slope through that process. However, once it reverses down the reverse slope far enough, then basically the ice shelf itself is completely gone, and you develop an ice cliff that, if it exceeds 800 meters in thickness, with about 90 meters above sea level, then the ice sheet, the cliff itself becomes physically unstable and starts to fracture and break just by mechanical processes. And once that starts, then you lose mass very, very rapidly, and the thing retreats very, very quickly. So it takes over MISI, if you will, with respect to causing even faster ice retreat down the reverse bed slope. So that's the new physical mechanism. Now, let's look at a couple things that DeCanto and Pollard came up with for this study. First of all, under the RCP 8.5 scenario, they found with their climate model, a global model, then they used a regional model over the ice sheet, driven by the global model for RCP 8.5, that in that particular model configuration, by the middle of this century, they started to see sufficient surface melting to cause meltwater production and hydrofracturing of the ice shelves. So this process, this mechanism in their modeling scheme with the models they use, driven by RCP 8.5 forcing, caused the MICI process to start this century. Okay, so that's key point number one. And then secondly, the model parameters that they used were basically derived from experiments they did to try to simulate past times of high sea level during the Pliocene, when Ken Miller has worked on that period of time, and during the last interglaciation, which Bob Kopp has worked on as well, so warmer periods than present, and sea level was higher than present, and so they did their modeling experiments to try to reproduce these periods of time. And with those simulations that met these criterion for these amounts of sea level rise, they used those parameters for their projections in their models, their model projections. And so for Pliocene sea level, they were looking at a target. What they targeted was to get a model simulation that fell within this range of sea level rise, above present, 5 to 20 meters. And for the last interglaciation, LIG, they were targeting this amount of sea level rise from Antarctica, 3.6 to 7.4 meters. And once they had a number of simulations that met these targets, they used that as an ensemble framework to derive their parameters and the uncertainty around their projections using those parameters. Okay? So let's look at their projections. This is for a case with a low Pliocene sea level target, as they call it, where sea level wasn't quite as high in the Pliocene as possible within that range, and with the same range of last interglacial sea level. And when they target those sea level, and then they come and they run their climate model to get the Mickey process started this century, then these are the projections they come up with just from Antarctica discharge. So RCP 8.5 is shown in red. Again, we'll just focus on that. And from that, they get 0.64 plus or minus 0.49 meters by the end of the century from Antarctic ice dynamics. Now, arguably, that's still within our allowance of AR5, several tenths of a meter. And if you read the chapter, you'll see that with the numbers we did assess that it is within that range. But when they target a high Pliocene sea level value, using the same last interglacial sea level values, this is where they end up with, for the end of the century, just from Antarctic ice sheet. 1.0 Antarctic ice sheet dynamics is over a meter of sea level rise with an uncertainty. And arguably that is higher than our allowance that we allowed for, or provided of several tenths of a meter, okay? So let's do an IPCC assessment of this study, and in two ways. First of all, as I mentioned, in their modeling scheme, with the models they used, a global climate model and a regional model, and the regional model was used to drive any surface melting that developed on the ice shelves, which they then found for RCP 8.5 started to develop by the middle of the century and give rise to the Mickey process. First of all, we did assess that possibility in the chapter of this surface melting occurring during the century. And with the studies that existed at that time, there was a very low probability that that situation would develop, okay? So they came up with in their modeling scheme, this process developing. Our assessment of other studies that existed prior to them found that that mechanism was not going to occur during this century. Now, more recently, but before DeConto and Pollard, just published in 2015, was this paper by Trussell et al., in which they used an ensemble of CMIP-5 climate model experiments, most suitable, they said, for Antarctica, and then used those model simulations to drive their regional model, which is called RACMO, which is a very sophisticated model that's been developed specifically for use on Antarctica and Greenland ice sheets. And it's been validated and used a number of different ways and times in that case. And when they drove CMIP-5 experiments with RCP 8.5 forcing through their RACMO model for the end of the century, this is the melting that they get on the ice sheet and the ice shelves. And you can see there's kind of a concentration of melting in the Antarctic Peninsula, but very little around the rest of the ice sheet. And the magic number in their threshold number for getting sufficient surface melting to cause ice shelf collapse was about 750 millimeters per year of meltwater on the ice shelf. So just look at the yellow and red colors, and you can see very little of that. In fact, less than 10% of the ice shelf areas around the ice sheet, other than the Antarctic Peninsula, experience this amount of melting. So, two things. So the second thing, with regard to DeConto and Pollard, was their target they used for the last interglaciation sea level from Antarctica, which is this amount. And the way they derived this amount was by assuming that the other contribution to explain the full sea level rise of the last interglaciation came from Greenland, but that Greenland contribution was only about 1.5 to 2 meters. Okay? So then if we look at all the studies that I've uncovered and that were published, mostly summarized in a paper a couple years ago in Dutton et al., and then another couple added on here. So we're looking at study across the horizontal, and then sea level from Greenland ice sheet. And you can barely see it, but the blue is up to the 2 meter contribution assumed by DeConto and Pollard. And you can see a majority of studies are suggesting quite a larger contribution from Greenland, which would mean the contribution from Antarctica was less. And so I would argue that if you put in those lower numbers from Antarctica in their model experiments, and they have the numbers there, but they don't show the projections associated with them, but logically that would lead to a lower projection for the future from Antarctic ice sheet if they had considered these higher possibility numbers from Greenland ice sheet. So my conclusion is that this DeConto-Pollard paper should be used with great caution at this point. Many more papers will appear by the time Bob finishes up the AR6 in 2021 that will be able to assess this conclusion in more detail and look for consistency and see if these high numbers are in fact going to hold up or not. But in the meantime, it's one study that is largely inconsistent with a lot of other evidence. So I'd recommend strong caution in using these numbers at this point. Okay. Okay. So I want to move on to the long term. And so in AR5, we concluded it's virtually certain that sea level rise, global mean sea level rise, will continue for many centuries after 2100. The main challenge that we had for making an assessment of what those numbers might be was the very limited number of ice sheet dynamical models that existed that included all the proper physics to assess the sort of long-term behavior of ice sheets over this longer period. So although the conclusion is very robust, virtually certain that sea level will continue to rise, we couldn't really put any firm numbers on how much it might rise in the future beyond 2100. Now, since then, several studies have come along that have long looked at this longer commitment to sea level rise. Now, a number of studies had looked at it beforehand from thermal expansion, but none had really looked at it in a way with sophisticated ice sheet models for the ice sheet dynamical contribution. So these three studies were published in 2015, and then this one that I led in 2016 did look at this contribution. In this case, the first two studies looked at the contribution from Antarctic dynamics. In this case, we looked at all the components except for land water. So we looked at the ice sheets, glaciers, and thermal expansion. And I'm going to focus on the results from this study in the remaining part of this discussion of long-term sea level. So what we did was, again, we used 4 scenarios. And basically, as in the case of most of these scenarios, it just represents a pulse of carbon that's emitted over a period of time of a varying amount. And the 4 pulses that we looked at, so here's the historical period up into the future to 2300, are shown in terms of the total carbon emissions for the 4 scenarios. So a lower emission scenario and a high emission scenario and 2 intermediate emission scenarios. And just for comparison, these are the corresponding emissions for the RCP 4.5 and the RCP 8.5. And you can see our high-end emission scenario is very similar to the 8.5 scenario. We didn't have something as low as 2.6, but otherwise that's just for comparison. So basically, then we used 2 models of intermediate complexity that had the carbon cycle in them. And with these carbon emissions, ran those models for 10,000 years to come out with both CO2 concentrations and surface temperature for the next 10,000 years. And then we use those temperature forcings to drive the glacier and ice sheet models, and then the thermal expansion comes directly out of the models themselves, out of the intermediate complexity models. So let's put this in perspective. So we're looking at 20,000 years ago on the left, to 10,000 years ago in the future. And what I'm showing now is the known CO2 record from ice cores that goes from the last glacial maximum 20,000 years ago through the present interglaciation to the present. And then this is two reconstructions of global temperature through this period of time that combine, we splice them together. And so what you see is that the ice ages were lower CO2, colder temperatures. We came out of the ice age, CO2 rose, temperatures warmed. And then this has been the present interglaciation. And then with the climate models, we came up with these CO2 concentrations for those 4 scenarios with the corresponding temperature, global mean temperature projections. So on the above is the CO2, and notice the scale change on the CO2 label here, or axis. So it's going from 300 and then it jumps up to 1,000, 2,000. And so you could see that there's our low emission scenario, our high emission scenario, and the intermediate ones in terms of CO2, and then for corresponding surface temperature response to that. Now, using this to drive the ice sheet and glacier models and thermal expansion to get the global mean sea level, let's put this in perspective what's happened in the past 20,000 years. When we came out of the last ice age, the last glacial maximum, large ice sheets in the northern hemisphere, and this is a record of sea level with various proxy records, and this is from Lambeck et al. So sea level was much lower, about 130 meters lower. Sea level rose as the planet warmed. Sea level reached present about 5,000 years ago or so, and has largely been the same since then with some variability. And then if we look at the projected sea level with those 4 scenarios, we end up with this. Now at this point, we don't have big ice sheets to deal with. We only have Greenland and Antarctica. But we still end up with basically Greenland ice sheet is gone. And for the highest scenario we looked at, which would be equivalent to RCP 8.5, very little of the Antarctic ice sheet remains. And if you look at the range of the 4 scenarios in terms of the global mean sea level response, it's on the order of 80 to 180 feet of sea level rise. And again, it's what's reflecting is that there's less ice to deal with on the planet than there was at the last glacial maximum. If there was as much ice for those kind of forcing, we'd probably end up with much higher sea level. But this is what we get. Okay? So recently, we've taken these numbers and come up with a carbon budget for global mean sea level rise. And so what we're looking at now is global mean sea level on the vertical axis and cumulative carbon emissions, in this case plotted from 450 gigatons of carbon up to 1,000 from pre-industrial. Okay? So this is cumulative CO2, how much carbon has been emitted or will be emitted across this range here. And then using our results, we've come up with these sea level functions related to cumulative carbon emissions. And so this is 2100 down here. This is from another model result by Alex Knowles using RCP scenarios. This is from Alex Knowles as well. And then these 3 other ones are from our results. And what we're basically doing is marching through time, 2100, 2300, 3000, 4000, and 9000. And if you follow any one of these timelines, and it's easiest just to look at the most extreme one, let's look at the 9000 timeline, then what you see is that as carbon emissions, cumulative carbon emissions increase, you would expect sea level rise to increase as well, reflecting the higher CO2. But if we pick any given carbon emission, cumulative carbon emission value, then you see through time, the sea level is rising for that. And this is just reflecting the long inertia in the sea level response to the forcing. So it takes a long time for the sea level to reach, as you saw in the previous time series, to reach at sort of a maximum amount. But what we're looking at here is basically committed sea level predicted for any given cumulative carbon emission that you can come up with from pre-industrial. Then we extended this, I ended at 1,000 gigatons of carbon, and you'll see why in a minute. But if we extend it out to the high end of the emission scenarios we looked at, so here's looking at 1,000 gigatons out past 5,000 gigatons. Again, you see that for any given time horizon, sea level rising is a function of the amount of carbon in the atmosphere. But for any amount of carbon that's been emitted, then you see the commitment to sea level increasing with time. Okay, so I want to move on to nearly the end, the implications. And so the implications, sorry, it's a nice picture. I'll let you look at that for a minute. Okay, so first of all, how are we doing? with regard to carbon emissions. So this is from the latest Global Carbon Project result, showing from 1990 to 2017, the amount of CO2 emissions and gigatons of carbon dioxide per year. And so here you can see in 2016, people were starting to think, oh, maybe we're just starting to bend the curve or level off, and then 2017 came along and popped up a bit. But what you can see is that carbon emissions per year, and thus cumulative emissions obviously have been increasing, but that the amount of carbon emissions per year has been accelerating more recently. So let's think about this with respect to that carbon budget. This is, in red is showing the total cumulative carbon emissions since pre-industrial up to 1990. So it's about 456 gigatons of carbon from that Global Carbon Project assessment. And what that shows you then is the commitment to sea level for that amount of carbon emissions from, in this case, 2,300 up to 9,000 years into the future. So we've already committed ourselves to some amount of sea level, and we knew that. Okay, but this is the first one to include the ice sheet contribution in addition to thermal expansion. Now let's look at the carbon emissions that have been released just in this century up until now, and the impact of that. And that slides us over from emissions up to 1999 to emissions up to 2017, which then slides us up in terms of this much more sea level commitment. So every year we wait, we have that much more sea level commitment ahead of us. Okay? Every year we wait to reduce and go to negative emissions, I should say, we have that much more committed sea level. So let's ask the question, where are we going? And these are different scenarios of emissions of fossil fuels and land use change, which is the main things we're looking at here. From 1980, so there's the historic record in black. 2017 is the red dot there. And then from there we go on into these different what-if scenarios. And these are based on the SSP database. So we have one scenario that's strong mitigation and brings carbon emissions down to 0 before the end of the century, limiting amount of temperature warming to somewhere less than 2 degrees, or more of a business as usual type of scenario, which is I've lost my pointer. That's okay, you can see, just follow the upward trajectory, and that puts us in there, and then these intermediate scenarios. So this is this whole idea about cumulative carbon emissions and temperature that was introduced or assessed by the AR5 was really the fundamental basis for the Paris Agreement. And the Paris Agreement in 2015 proposes to hold global average temperature to well below 2 degrees above pre-industrial levels and pursue efforts to limit the temperature increase to 1.5 degrees Celsius. So with the cumulative carbon budget that's been established for temperature, they know exactly how much carbon we have still to release or even go negative in order to achieve these goals of the Paris Agreement. And so based on those types of scenarios, this would be, for example, one scenario that's required for carbon emissions through the rest of the century to avoid 2 degrees of warming. These are just different scenarios, but they all sort of meet this goal of starting to drive down emissions towards negative and reaching negative after 2050. In this way, we will achieve the goals of the Paris Agreement and stay below 2 degrees. So we know what these emissions are to achieve these goals. These have been tallied up extensively. And first of all, when the countries that signed the Paris Agreement proposed what they call nationally determined contributions by which each of them would contribute X amount of carbon emissions. And they did this, if we look at the period of which most countries have done this for 2000 to 2030, then this is the range of those emissions that they've now have in place to meet the goals of the Paris Agreement. It's shown by the red bar. And you can see it's well above the carbon emissions needed to keep below 2 degrees. So everyone knows that we're not on track to meet the Paris Agreement at this point. We need to do more, okay? But now we can go to our carbon budget versus sea level figure and look at this with regard to some of these emission targets. And so that's shown in the gray bars with the different targets. So the less than 1.5 degrees Celsius, in order to achieve that, that's the range of emissions that are required from pre-industrial, and that's the sea level commitment that that target would give us. If we look at the nationally determined contributions for the period 2000 to 2030, just what they're proposing to do now, up to the year 2030, not beyond that, that's the sea level contribution from that. And then if we look at the emission targets to keep below 2 degrees Celsius, those are the sea level committed sea level associated with that. Okay, so to conclude, some take-home messages. For a business as usual scenario, that is the RCP 8.5, if we don't get to 1 meter from Antarctica by dynamics by 2100, then it will likely happen soon after, okay? So this 2100 year sort of target is important in a number of respects, but it's really kind of also arbitrary to pick on 2100. So Antarctica gets there before then, after then, at this rate, it'll get there if we don't do something about it. There is hope, though, that we will veer off this trajectory, largely because of the Paris Agreement and other reasons, many other reasons. Hopefully we'll start to see a bend in the emission curve and draw as such that it will start to decrease towards the century and maybe reach zero emissions. So maybe Antarctica won't get to that point. So even if carbon emissions reach zero by the end of the century, though, sea level rise by 2100 is just the tip of the iceberg. And we still have a commitment to a much larger rise occurring well after 2100. And again, this has been known, the committed sea level from thermal expansion has been known. We've simply added in the contribution from ice sheets. The scope of this multi-millennial commitment is what it is to sea level rise, as well as to other profound impacts on global climate, ecosystems, and human societies, will be based on policy and economic decisions made in the next few years to decades. That's the amount of time we have to veer off the business as usual and get down to something that's more manageable in order to avoid the worst case scenarios I was showing you. But we don't have a lot of time to do that. Okay, so it's not just the commitment to 2100, it's the long-term commitment we're talking about. And then finally, I just read this opinion piece by Paul Krugman in the New York Times, which is a place where I go for a lot of solace these days. And this was just the other day where Paul Krugman wrote, "There is no longer any reason to believe that it would be hard to drastically decarbonize the economy. Indeed, there's no reason to believe that doing so would impose any significant economic cost. For now, the problem isn't technology, it's politics." Okay, so with that, I'll leave on this beautiful image of Antarctica and take questions. Yep.
So that mechanism for collapse due to the overlying meltwater in Antarctica. So I saw what you said, hydraulic fracturing. So it's like a freeze-thaw cycle, like the meltwater gets into the. Okay.
It's not freeze-thaw. It's just that the water gets into the crevasse, okay, and the weight of that water itself forces the crevasse to open up even more.
Okay.
And that's what they mean by hydrofracturing. Yeah.
One of your take-home messages was about policy, economic decisions, and politics, the last one. Have you come across any promising individual actions that people can take, assuming that politics is not going to solve the problem? There has to be individual lifestyle changes. Now, I'll give you an example, which might sound a lot outlandish, but for example, the use of methane, people call it natural gas. Okay, people are using clothes dryers to dry their clothes. I have no idea what percentage of carbon emissions is caused by the burning of methane in people's homes. But other than something like that, which might be a small speck, have you come across any discussions about what individuals can do other than relying on governmental decisions to combat global warming?
You know, I think there's a number of those types of recommendations for personal action, both with regard to reducing your carbon footprint and to somehow encourage a reduction of carbon footprint in other ways beyond politics. But I don't know the numbers of what the estimates are if everybody was to reduce their carbon footprint by X amount, how much that would matter or how much is needed to do that to matter. Bob may keep track of those numbers. Bob, where are you? There you are, hi. May keep track of those numbers more closely than I do. I know they're out there, I'm sure. Okay.
Well, I think the key point to take away from your study is right there. To stop warming, you need to get global emissions to zero.
Right.
Right? And that's not an individual action.
Yeah, so I was getting there, yeah. So, but that is the point, is that we need to go to -0 or negative emissions. And so reducing our footprint is not enough, because the problem is that CO2 we release now stays in the atmosphere for a long time. So every amount we release, whether it's less or not, is still going to be up there and still have a consequence. So the quicker we get down to negative emissions, the better. And I don't think we're going to be able to do that through personal choices. Another major thing that's happening with independent of politics is economy. And that's going to take a while. It's not going to happen in time, I would suspect. But nevertheless, it's happening, and there's going to be a major economic drive to move to different sources of energy. So, Bob, do you want to espouse any more on that? Okay. Yep.
So you talked a little bit about negative emissions.
Yeah.
Are there any time scale issues between sort of the feedback around sea level rise and negative emissions? Like, do negative emissions just reduce carbon and therefore less sea level rise, or is there a certain amount of positive feedback once the ice sheets start retreating that negative emissions would not solve?
So both. So the dynamical response of ice sheets, to a large extent, becomes untethered to climate. Although people are trying to come up with these geoengineering solutions even to deal with that. But for the at this point, I think most of these ideas are just far from reality. Not to say they're not possibilities, but they're not going to happen anytime soon. So, but as far as the surface mass balance part of it, in fact, what's going to happen is Antarctica, the contribution from Antarctica is actually, from the dynamical contribution, is offset by the fact that it's going to be gaining mass for some foreseeable future as the Antarctic continent warms, could hold more moisture as snow falls. So in our assessment, in fact, when you looked at the Antarctic surface mass balance contribution, it went negative for the century as opposed to dynamics. Greenland is a situation where the surface mass balance response could cross a threshold that becomes irreversible unless we engineer or start to lower CO2 in the atmosphere in some way. So going to negative emissions over a sustained period of time to actually start reducing CO2 in the atmosphere, I think is an area that's ripe for research in terms of what that means for ice sheets. DeConto and Pollard did look at it a little bit, and more people, I'm sure, are doing that, and I would like to do that. So, yeah. Yeah.
So you already talked about basically Greenland and Antarctica. What about the Himalaya ice sheets, the North American, Canadian Rockies, that kind of thing, ice sheets? Factoring that in. Is that just de minimis?
So if you add up the sea level contribution from all land ice glaciers, exclusive of Greenland and Antarctica ice sheets, today it amounts to about 40 centimeters of sea level. So it's in our numbers, but it's just dwarfed by all the others, so it's insignificant. And essentially, well, no, it's not good news because most of them will be gone by the end of the century at the same time, so yeah. But it's not a big factor with regard to sea level rise. It is a lot of regional importance to those things with respect to local water resources and stuff, yeah. Yeah. Question?
Yeah, we know there's a complex and large subglacial hydrological system in Antarctica and under continental ice sheets in general, probably. What do we know? Can you summarize or bring up to date the current knowledge about how that system might change in the future and how that might contribute in some way to add on another mechanism to accelerating or decelerating the rate of loss in West Antarctica, for example? Because the DeConto paper doesn't really talk about that, I think.
No,
right?
no. So the question is subglacial hydrology a possible factor in influencing ice sheet response? It's been looked at a lot from Greenland because some 10 years ago or more now, they discovered that surface water from surface melting of the ice sheet was reaching the bed of the ice sheet within days through these moulins or holes through the ice sheet that went 2,000 meters through the ice sheet, meaning that the surface response of meltwater was reaching the bed immediately, and the potential there was, everyone was then thinking, well, is that going to lubricate the base of the glacier and allow it to flow faster and thus flow into the ocean and accelerate the loss? So that's been looked at a lot and by a lot of studies since then, and I believe that the current understanding is that that effect is actually minimal. That it's because the hydrologic system in an ice sheet, that hydrologic system can respond quickly to changes in discharge just by growing or closing the cavities. That time scale of that is on the order of weeks or so. So it can adjust to and change the pressures at the base of the ice sheet that might influence ice flow fairly quickly and not cause a major factor. I suspect the same would be true of Antarctic ice sheet. It hasn't been looked at there that I know of, but I suspect it to be the same. Yeah.
Are sources of CO2 that may not be directly linked to anthropogenic, like methane, hydrate, permafrost melting, does it include any of these calculations?
This is just carbon emissions, fossil fuel. Yeah. No, not. I mean, we don't know. I mean, methane. So a lot of these greenhouse. This is a couple things. One is a lot of these other greenhouse gases, like methane, are short-lived in the atmosphere. So they don't really have the longevity like CO2 does. So they have a short-term effect, which could be important, but they won't have the sustained effect. But in that short term, things like methane could have potentially a very, as many people know, again, I don't know the current understanding of the potential for permafrost thaw and methane release. I think it's considered relatively low possibility, but it is a possibility. So if anyone want to chime in and knows more about that, please do.
I was going to say the permafrost, it's not just permafrost methane, it's permafrost carbon. It's a significant carbon dioxide source, either directly or once it oxidizes. Most of the studies when I last assessed it was a year or two ago. Actually, this was last year. Where, it's just like it has a potential to be a 30 to 50% increase in overall warming. It's not, there's not any indication that it would be the dominant driver, but it's a significant positive feedback. And now you just look at your results and say, well, great, that's more carbon emissions, and that's what you did. Yeah.
Yep.
It's actually kind of hard to imagine getting to zero emissions based on changes in energy sources, especially given population increase and such. So what is the current thinking about the likely contribution of carbon sequestration technologies?
So not going to be available in time.
But in the models, that negative emissions technology is all represented as carbon capture and sequestration. So where he shows negative emissions, that is effectively bioenergy coupled to carbon capture storage on a scale comparable to the current fossil fuel extraction infrastructure.
In this scenario.
Yeah. In all of the scenarios that you're showing that are consistent with the Paris Agreement.
But my understanding otherwise is that whether or not that technology is going to reach that point is another question. So,
Do you think it's effective to take to the greater audience outside of our scientific community the risks that you're describing or the challenges in the future of global mean sea level change, or emphasize the tip of the spear is going to be at local places? We've heard talks here about New York, Norfolk, Miami being very vulnerable, and they're going to be the places where economics and politics, I would think, would be most keenly debated and could be the hotspots. Should we be emphasizing as scientists those future scenarios or the ones in a more global sense?
We did address that to some extent in this paper, and again, I didn't have time to cover everything, but this to some extent addresses that, I think. This is for the low-end scenario we looked at. The long-term committed sea level rise, areas in purple are completely underwater. Areas, yellow cities or mega cities of 10 million more, they're basically underwater. And this doesn't account for the extreme events, which is a whole other thing. And this also accounts for This is not global mean sea level rise. This is the regional sea level rise from all the factors that cause sea level to vary regionally as well. So this is based on that. So yeah, absolutely.
Well, do we get dismissed as alarmists by stressing these hotspots as opposed to a more measured model area global? I'm asking for your advice.
Do we get dismissed as alarmists for focusing?
I've gotten audiences saying to me, well, I don't quite care what happens to the Mekong Delta. And it doesn't hurt America first.
Right. Well, there's America, and you know, and this is the low end. Now, this weekend we have something coming out in the New York Times you might look at as well that looks at the high end, just as a what-if type of thing, which looks at state-by-state level thing. So, good point. Where it hits the most makes the biggest difference, and yeah, I certainly agree with that. Okay, thank you again very much.